we're going to take a look at vector analysis and specifically vector fields. So we want to be able to understand the concept of a vector field. It might be helpful to refresh yourself on basic 2D vectors before continuing on with this lecture. A great place to do that is to go look over at Khan Academy just to refresh yourself. Then we're going to determine whether a vector field is conservative. We're going to find the curl of it, and then we're going to talk briefly about the divergence of a vector field. The divergence isn't so important in this lesson, but it's a good thing to help wrap your head around mentally. So if we're looking at vector fields, we're going to call those functions that assign a vector to a point in the plane. So I've got a function that identifies to a point in the plane, or a point in space, so I'm talking about 3Ds here, that are called vector fields, and they're useful in representing various types of force fields and velocity fields. Obviously, we're not talking about Star Trek here with force fields, but we're talking about like magnetic fields and things like that where forces are being applied. A vector field over a plane, so over a two-dimensional surface with region R, is a function f. So we're going to use the letter f a lot here, that assigns a vector of function of x of y to each point. A vector field on a solid region, this is going to be more than 2 dimensions, is a function that assigns it with x, y, and z, because we're 3-dimensional, to each point q. So differentiation there in 2D versus 3D. The gradient is one example of a vector field that you're going to see a lot in your assignments. So for instance, if I have a function of x, y, and z, that's x squared plus y squared plus z squared, then a gradient of that, so the upside down triangle, is what we use to represent the gradient. So if I have the gradient of that, I have the function where x is a variable, y and z are constant, and that's going to have I. So if you're refreshing yourself on vectors from your two-dimensional non-calculus based courses, I and j, I is typically the x-axis, j is typically the y-axis, and so here logically k becomes the z-axis. Plus you've got the function defined with y as a variable, z is constant times j, and then last z is the variable, x and y are the constants with k. So let's just say I've got a vector field in space where I have 2x because x is a constant. Let's say if I'm looking at, and where does the 2x come from? It comes from here. So I'm going to treat, in the first one, x squared like a variable, which is 2x, and then these are constants, so they go away. In the middle one, I'm going to treat y squared like a variable, so the derivative of that is 2y, and the other two terms go away. So that's where this comes from. Think of this like partial derivatives. So this is a vector field that's occurring in a 3-dimensional space. If I look at the components, remember components would be the I is one component, j, and k of this particular vector field are described by 2x, 2y, and 2z. I could also have a vector field where I have m, n, and p involved. So this function is continuous at a point if and only if the components that are described by m, n, and p are continuous themselves. So this is kind of similar to two-dimensional math. If the components are all continuous, then the outcome is also going to be continuous. Some common physical examples of vector fields, like we talked about before, would be velocity fields, gravitational fields, electric force fields, magnetic fields, even potentially movement across meteorology when you're looking at hurricane tracks and things like that. Velocity fields are really useful to us because they describe the motion of a system and particles in the plane or in relation to space. So as we get into 3-dimensional objects, it's really nice to have a vector field because it shows us what's happening to that 3-dimensional object. So in 15.1, I'm showing a vector field that's determined from a wheel that's rotating around an axle. If you look at the velocity vectors, and I'm looking at the locations of their initial points, the further it gets from the axle, the greater its velocity. Now, how do I know that? I know the velocity is greater because the incline of the line is more. So if I'm looking at the incline of the line here on the outside versus the incline here on the inside, those are almost horizontal with little to no slope. Here I start to see some really steep inclines as I'm getting further out from the axis. They're also determined by the flow of liquids through a container or by air currents around a moving object. So if we're talking about the velocity of a car or of an airplane, a vector field is formed by the air currents because it's having to adjust and go up and over the car or up and over the plane. So these are tied very closely to physics because gravitational fields are defined by Newton's law of gravitation. And if you're wondering what that means, Newton's law of gravitation says that the force of attraction that's exerted on a particle with a certain mass located at a given point and by a particle of mass 2, so I have two particles involved, at the origin is given by this equation here, where g is the gravitational constant and u is the unit vector in the direction of the origin. So I still have my x squared, my y squared, my z squared, but now I've got this new constant g, and then I have my mass 1 and mass 2, so that's what the m stands for. In figure 15.3, if I'm using a gravitation field, I can see that this is always pointing towards the origin, and the magnitude of this is going to be the same at all points that are equidistant to the origin. So if I'm looking at those lines, they do appear to all have the same inclination and the same direction, which is why we're saying they're the same magnitude. A vector field with these properties has a special name of a central force field. So let's look at using the position vector. In a position vector, my coefficients are all going to be 1, or a unit vector. So a position vector is a description of a unit vector. I can also have position vectors with different coefficients, but this one here is the unit vector. If I'm looking for the point itself, I can write the gravitational field as my gravitational constant times my first mass and my second mass times my r over the magnitude of r, and then I've also got divided by the magnitude of r squared. So remember, magnitude is signified by the double lines, and that's going to be the square root of the components squared and added together. So in electric force field, we use Coulomb's law, which states that the force exerted on a particle located at a specific point by another particle is given by this equation. So if you'll notice, this equation has the difference of there's a c value, and c is a constant that depends on the choice of units, and then also on Q1 and Q2. So what's important to notice is that electric fields have the same force as a gravitational field, so that we have something divided by the magnitude squared. Now the magnitude squared is happening with looking at negative numbers and ensuring we always wind up with a positive number here. So such a force field is called an inverse square field when this occurs. So if I look at the definition of this, I've got my k, which is going to be part of that position vector, and I've got k divided by the magnitude of r, so the radius, that would be the square root of x squared plus y squared plus z squared, times my unit vector, which is calculated by doing the radius divided by the magnitude of the radius. If you don't remember how to find a radius from components, great review to pop over to Khan Academy. So if I'm looking at this example and I want to sketch a vector field, this is very similar to sketching a slope field. So if I want to sketch the vector field given by this equation, I have two components here, which is kind of nice. It simplifies things for you. Then I could plot the vectors at random points, but it's typically better to plot vectors of equal magnitude. So this means I need to find the corresponding level of curves in the scalar field so that the vectors of equal magnitude lie on circles. So I'm going to find the vectors of length c by doing the radius process, so the square root of x squared plus y squared, and then I'm going to get x squared plus y squared equals c squared because I squared both sides. So if I want to start sketching, I'm going to be able to use that formula and to plug in numbers like 1, 0 and find out, well, where is 1, 0 here? And then I can sketch 1, 0 and also take a look at the magnitude or the incline based on the outcome. So if I'm at the point 1, 0, it's right here. And at 1, 0, I just get component J. And if we go back here, component J is going to be related to an x value. So if my j is constant, because I just have j, there's no I here, my j remains constant, then I'm going to simply have a vertical line. So that's the differentiating factor here, is there's just a vertical line because my slope is just going to be for x equals 1. Here I get negative I at 0, 1, which would be here. And if I have a negative y component, that's going to be a horizontal line. So that's where all of this is playing into the diagram. We're going to briefly just talk about a conservative vector field. This isn't going to be really used in the homework a whole lot, but I just want to touch on it quickly. Some vector fields can be represented as the gradients of a differentiable function, and some actually can't. If you cannot represent it as a gradient, then it is going to be called a conservative vector field. So if I look at the vector given by 2xi plus yj, and I would say it's conservative. So to say that, I'm going to consider the potential equation. This is given to you. This is not a part of something I calculated, of x squared plus 1/2 y squared. Well, because my gradient is equal to that function, it follows that f should be conservative. So if I'm giving you a vector field and I'm saying, hey, this vector field is conservative, 2xi plus y, if I look at that, then I differentiate to get here, x squared, the derivative is 2x, 1/2 y squared, the derivative is y, so this function here is the derivative of this function here. If the derivative is conservative, it's going to follow that the original is also conservative by definition. If I look at every square field, those are all going to be conservative all the time, and there's a little proof there on why that actually is. So if I want to test for a conservative vector field, I'm going to use partial derivatives. So that means the partial derivatives must be equal between the two. So just really quick as I look at an example of this, if I look at this vector field that I'm given, x squared y I plus xyj, it's not going to be conservative because they're not equal. I've got x squared and I've got y. Those aren't equal. That's a linear term and a quadratic term. Here, the partial derivatives are both equal to 0. So that means that this is conservative because I get the same value out of it. So now let's look at the curl of the vector field. So the definition of the curl of the vector field is given by this equation. Notice that m, n, and p are making a comeback. And the curl is going to be the cross product of the gradient with the original function. So the cross product, we can go back to trig and do that, or we can utilize the formula that's actually here, where I'm subtracting the partial derivatives with the components I, j, and k. So the cross product notation is used here for curl, and it comes from viewing the gradient as the result of a differential operator that's acting on the function x. So you'll notice in your textbook things go back to matrices quite a bit, and occasionally we dodge the matrix and we can actually use the formula. This matrix is simply the proof for the formula at the bottom of the page. So this is going to be the formula for remembering a curl, but you would get to it from finding the determinant of that earlier matrix. So on your homework, feel free to skip the matrix step and to use that formula. So if I want to find the curl of the given vector field here, that's going to be 2xyi plus x squared plus z squared j is 2yzk. And so we want to know, is f irrotational? And so the solution is to find the curl of my function given by f of x, y, and z. I'm going to take the gradient and do the cross product. So in order to do that, I'm going to put my partial derivatives into the matrix, and then I'm going to actually put the components into the matrix. When I do that, I'm going to do the determinant, and when I do the determinant of a 3 by 3, I'm going to reduce that into a series of determinants of 2 by 2s, which I could also get to from using that formula and avoid the entire process of doing this piece. So you can skip that determinant and go further down. So because the curl is equal to 0, we can also say that it is irrotational. And so if I want to test this, test the curl is irrotational, I'm always going to set it equal to 0 to see if that gives me a true statement.